The bouncing cosmology theory. A new perspective on the universe. What if the Big Bang wasn't the beginning of everything, but just a phase in an ongoing cosmic cycle? A revolutionary theory known as bouncing cosmology suggests that the universe undergoes continuous cycles of contraction and expansion, challenging the conventional idea of a singular beginning. This concept could help answer some of astrophysics' biggest mysteries, including the nature of dark matter and the formation of black holes, suggesting they may have originated in a prior cosmic phase, before the Big Bang itself. With the advancement of future gravitational wave observatories like LISA, Laser Interferometer Space Antenna, scientists hope to test these groundbreaking ideas, potentially transforming our understanding of the universe. In this discussion, we will explore what bouncing cosmology is, how it may help solve the dark matter mystery, and what future discoveries could mean for modern science. A cyclical universe. The bouncing cosmology model. Unlike the traditional Big Bang theory, which proposes a singular beginning followed by rapid inflation, the bouncing cosmology model suggests the universe follows a repeating cycle of contraction and expansion. Instead of emerging from nothing, the universe undergoes a phase of contraction, reaching an incredibly dense state, before undergoing a bounce that initiates the expansion we observe today. This idea challenges the long-held belief that the universe began as a one-time, unrepeatable event. The Big Bang model, while explaining the observable expansion of the universe and the existence of the cosmic microwave background (CMB), leaves unanswered questions, such as what caused the initial singularity and why the universe appears so uniform on large scales. Bouncing cosmology provides an alternative by suggesting that the universe's current state is just one stage in an endless cycle, eliminating the problem of a singular beginning and implying that the laws of physics we observe today may be deeply connected to conditions from a previous cosmic era. A key feature of this theory is the idea of a non-singular bounce, where quantum gravitational effects prevent the universe from collapsing into an infinite singularity. Instead, these quantum effects cause a rebound, leading to a new phase of expansion. Within this framework, what we refer to as the Big Bang is not the beginning of everything, but rather the transition from a prior contraction phase to our currently expanding universe. This cyclical process suggests that galaxies, stars, and planets may have roots in previous cosmic eras, influencing the structure and evolution of the universe across successive cycles. Mathematical models and simulations supporting this theory predict specific patterns in the distribution of cosmic structures, such as galaxies and the CMB, which could serve as evidence for this cyclic nature. Dark matter and primordial black holes. A new explanation. One of the most intriguing aspects of bouncing cosmology is how it could explain the nature of dark matter, one of astrophysics' greatest mysteries. Dark matter, which makes up roughly 80% of all matter in the universe, is inferred from its gravitational effects on visible matter and the CMB. However, it does not emit, absorb, or reflect light, making it nearly impossible to detect directly. Traditionally, dark matter was thought to be composed of exotic particles like WIMPs, weakly interacting massive particles. However, bouncing cosmology offers an alternative explanation. Dark matter could be composed of primordial black holes, PBHs, which may have formed during a prior contraction phase of the universe. Under extreme density and temperature conditions, small fluctuations could have led to the formation of tiny black holes immediately after the bounce. These primordial black holes could range in size from subatomic particles to several times the mass of the Sun. If these black holes were massive enough, they could survive Hawking radiation and persist to the present day, explaining the gravitational effects observed in galaxies and galaxy clusters. This idea bridges two major fields of modern physics, cosmology and black hole physics, suggesting that some of the gravitational influences we detect may originate from events before the Big Bang. If future observations confirm that dark matter consists of primordial black holes, it would not only solve a fundamental mystery in physics but also support the bouncing cosmology model, providing strong evidence that the universe is cyclical rather than having a single origin event. The search for evidence. Gravitational waves. To validate or refute the bouncing cosmology model and its implications for dark matter, scientists need direct evidence. One of the most promising methods is through the detection of gravitational waves, ripples in spacetime caused by massive cosmic events such as the collision of black holes or neutron stars. According to bouncing cosmology, primordial black holes formed during a contraction phase would have generated a unique spectrum of gravitational waves, distinct from those predicted by standard models. Upcoming gravitational wave observatories, such as LISA, Laser Interferometer Space Antenna, and the Einstein Telescope, will be crucial in detecting these signals. Unlike current ground-based observatories like LIGO and Virgo, which primarily detect high-frequency gravitational waves from recent cosmic events, LISA and the Einstein Telescope will be able to detect low-frequency gravitational waves, potentially originating from the bounce itself. Detecting these unique gravitational wave patterns would provide groundbreaking observational evidence for bouncing cosmology, challenging the traditional inflationary model and reshaping our understanding of the universe's origins. Such discoveries would not only confirm the cyclical nature of the universe but also help merge the fields of quantum mechanics and general relativity in ways that current cosmological models struggle to achieve. A new era in cosmology. The search for these primordial gravitational wave signals is already underway. Scientists are carefully analyzing data from existing gravitational wave detectors and preparing for the launch of next-generation observatories capable of probing deeper into the universe's history. While some intriguing candidates have been identified, more data and more sensitive instruments are required to confirm these findings. If proven, the bouncing cosmology model would redefine our understanding of the cosmos, revealing a far more complex and interconnected history than previously believed. Thank you for joining us on this fascinating exploration into bouncing cosmology and its potential to revolutionize astrophysics. From the nature of dark matter to the role of gravitational waves, this theory could provide groundbreaking insights into the universe's past, present, and future. If you found this discussion insightful, don't forget to like, share, and subscribe for more content on the latest breakthroughs in science and space exploration. Until next time, keep exploring the cosmos.